this module, you will learn about the ionic equilibrium in solutions. In this image, one beaker contains aqueous sodium chloride solution and the other contains aqueous sugar solution. How will you identify which beaker contains the salt solution and which contains the sugar solution? Obviously, the beaker indicated by the glowing bulb contains the salt solution, and the other beaker, where the bulb is not glowing, contains the sugar solution. Substances like sodium chloride, which conduct electricity in their aqueous solutions, are called electrolytes. And molecular compounds like sugar, which do not conduct electricity, are known as non-electrolytes. This classification of substances into electrolytes and non-electrolytes based on their ability to conduct electricity was made by the English chemist and physicist Michael Faraday. Michael Faraday further classified electrolytes into strong and weak electrolytes. According to him, strong electrolytes undergo dissociation completely when dissolved in water, while weak electrolytes undergo dissociation only to a limited extent. For example, HCl is considered a strong electrolyte as it undergoes dissociation completely when dissolved in water. An aqueous solution of HCl contains only H+ and Cl- ions. On the other hand, acetic acid is considered a weak electrolyte as it undergoes ionization to a very limited extent. An aqueous solution of acetic acid mainly contains unionized acetic acid molecules in equilibrium with a few hydrogen and acetate ions. Hence, the equilibrium involving the ions in an aqueous solution of a weak electrolyte is called ionic equilibrium. Ionic equilibrium can be conveniently studied under two headings: dissociation equilibria, solubility equilibria. Dissociation equilibria. The equilibrium between a dissolved undissociated molecule and its ions is known as dissociation equilibria. In general, dissociation equilibria involve either acids or bases. We deal with many acids, bases and salts in our daily lives. Even some food items contain acids. For example, orange juice and lemon juice contain citric and ascorbic acids. Tamarind paste contains tartaric acid. Curd contains lactic acid. Spinach contains oxalic acid. Salads which are flavored with vinegar contain dilute acetic acid. Isn't it amazing that HCl is produced in our body and helps in digestion? The bases commonly used in our daily life include ammonium hydroxide in cleaning liquids, magnesium hydroxide as an antacid, and sodium hydroxide in the manufacture of soap. Many compounds known to us may be classified as salts. The salt most familiar to all of us is sodium chloride, which forms an important component of our diet. Washing soda used for washing and baking soda, which is used in baking, are also the examples of commonly used salts. The word acid is derived from the Latin word acidus, which means sour. Acids exhibit certain properties in their aqueous solutions. They are sour to taste. They turn blue litmus red. They react with active metals like zinc and liberate hydrogen gas. On the other hand, bases display the following properties in their aqueous solutions. They are bitter in taste. They turn red litmus blue. They are soapy to touch. Arrhenius gave the first real classification of the chemical nature of acids and bases, which is popularly known as Arrhenius theory. According to his theory, an acid is a substance that contains hydrogen and ionizes in an aqueous solution to give hydrogen ions. For example, HCl contains hydrogen and ionizes in water to H+ and Cl- ions. The ionization of hydrochloric acid in an aqueous solution can be represented in the form of equation 1 or equation 2 as shown. As a bare proton, H+ is very reactive and cannot exist independently in an aqueous solution. Instead, it bonds to an oxygen atom of the water molecule and forms H3O plus the hydronium ion. A base is a substance that contains the hydroxyl group and ionizes in an aqueous solution to give hydroxide ions. For example, NaOH contains a hydroxyl group and ionizes in water to Na+ and OH- ions. The ionization of sodium hydroxide in an aqueous solution may be represented in the form of an equation as shown here. A hydroxyl ion, like H+, also exists in the hydrated form, like H3O2-. Although H+ and OH- exist in the hydrated form, for the sake of simplicity, we usually write H+ and OH- rather than H3O+ and H3O2-. However, the Arrhenius theory of acids and bases has some limitations. It is limited to aqueous solutions only. For example, HCl is considered as an acid only when it is dissolved in water and not in some other solvent such as benzene. Some substances exhibit the properties of a base though they do not contain hydroxide ions. For example, liquid ammonia behaves as a base although it does not contain any hydroxyl group in it. In an attempt to overcome the limitations of the Arrhenius theory, Danish chemist J.N. Bronsted and English chemist T.M. Lowry proposed a more general definition of acids and bases. According to the Bronsted-Lowry theory, an acid is a substance that exhibits a tendency to donate a proton, and a base is a substance that exhibits a tendency to gain a proton. In other words, proton donors are acids and proton acceptors are bases. Consider a generic acid-base reaction. Ha plus water in equilibrium with H3O plus and A minus ions. In the forward reaction, Ha donates proton to water and thus acts as a Bronsted-Lowry acid, while water accepts the proton and acts as a Bronsted-Lowry base. Did you notice that water, which acts as a Bronsted-Lowry base, has turned into a Bronsted-Lowry acid after accepting the proton, and the species Ha, which acts as a Bronsted-Lowry acid, has turned into a Bronsted-Lowry base after donating the proton? This is because a Bronsted-Lowry base, after accepting a proton, becomes a Bronsted-Lowry acid as it has a proton to donate. And a Bronsted-Lowry acid, after donating a proton, becomes a Bronsted-Lowry base as it now has room to accept a proton. The species that remains after an acid gives up its proton is called the conjugate base of that acid. Similarly, when a base accepts a proton, the resulting species is called the conjugate acid of that base. Thus, such a related pair of an acid and a base, which differ by a single proton, is called a conjugate acid-base pair. In the generic example that we saw just now, H3O+ is the conjugate acid of the base, H2O, and A- is the conjugate base of the acid, HA. Now, in the ionization of HCl in water, HCl acts as a proton donor and water acts as a proton acceptor. Hence, HCl and water are called Bronsted-Lowry acid and base, respectively. As you can see, in the reverse reaction, the H3O+ ion acts as a proton donor and the chloride ion acts as a proton acceptor. Thus, the H3O+ and Cl- ions act as Bronsted-Lowry acid and base, respectively. Observe that the H3O+ ion, H2O, and the HCl and Cl- ions differ from each other by a proton only. Therefore, you can say that H3O+ is the conjugate acid of the base H2O, and Cl- is the conjugate base of the acid HCl. In the dissolution of ammonia in water, the water molecule acts as a proton donor and the ammonia molecule acts as a proton acceptor. Thus, the water and ammonia molecules are called Bronsted-Lowry acid and base, respectively. In the reverse reaction, the ammonium ion NH4+ donates a proton to the hydroxide ion OH-. Hence, NH4+ and OH- act as Bronsted-Lowry acid and base, respectively. In this case, the OH- ion is called the conjugate base of the acid, H2O, and the NH4+ ion is called the conjugate acid of the base, NH3. However, even this theory had its limitations. The theory fails to explain some reactions that do not involve a proton transfer. For example, the neutralization reaction between the acidic oxide, carbon dioxide, and the basic oxide, calcium oxide, does not involve any transfer of proton. It fails to explain acidic behavior of electron-deficient molecules like AlCl3 and BCl3. In 1929, G.N. Lewis proposed a more general theory of acids and bases, which is founded upon the electronic theory of valency. According to this theory, an acid is any molecule or ion that can accept an electron pair to form a coordinate covalent bond with the donor. For example, H+, BF3, AlCl3, and SnCl4 act as Lewis acids. A base is any molecule or ion that can donate a pair of electrons to form a coordinate covalent bond with the acceptor. For example, NH3, H2O, and OH- ion act as Lewis bases. In short, an electron pair donor is a base and an electron pair acceptor is an acid. According to this theory, a neutralization reaction is simply the formation of a coordinate covalent bond between an acid and a base. For example, in the formation of NH3BF3 abduct, the boron of BF3 accepts a lone pair of electrons from the nitrogen of ammonia and forms a coordinate covalent bond. The Lewis theory had its limitations too. This theory fails to explain the strength of acids and bases. All the acid-base reactions do not involve coordinate covalent bond formation. For example, the reaction of HCl with NaOH does not involve any formation of a coordinate covalent bond. Generally, acid-base reactions are very fast, but in certain cases, the formation of a coordinate covalent bond is very slow. You have now reached the end of this module. In this module, you learned that the equilibrium involving the ions in an aqueous solution of weak electrolytes is called ionic equilibrium. The equilibrium between a dissolved undissociated molecule and its ions is known as dissociation equilibrium. Properties of acids: they are sour in taste, they turn blue litmus red, they react with active metals like zinc and liberate hydrogen gas. Properties of bases: they are bitter in taste, they turn red litmus blue, they are soapy to touch. According to the Arrhenius theory, an acid is a substance that contains hydrogen and ionizes in an aqueous solution to give hydrogen ions. A base is a substance that contains hydroxyl group and ionizes in an aqueous solution to give hydroxide ions. According to the Bronsted-Lowry theory, proton donors are acids and proton acceptors are bases. A related pair of an acid and a base which differ by a single proton is called a conjugate acid-base pair. According to the Lewis theory, an acid is any molecule or ion that can accept an electron pair to form a coordinate covalent bond with the donor.